she explained to me what that meant just a minute ago. So yeah, well, welcome to my talk. It's great to see a room full of people here, but that's what you get if it's a single-track conference, right? So this is my talk on the microservice architecture. And really what I'm going to cover is first just talk about the motivations for using microservices. Like what situations would you use them in, and what are the benefits would you expect to get from that? And then I'm going to talk about the essential characteristics of the microservice architecture, give a definition, and then just sort of talk about various aspects of the architecture and some adjacent technologies. And I'm actually going to finish up by talking about testing, because that's one of the super interesting aspects of this whole thing. Kind of mentioning some of the topics that Beth talked about earlier in her talk. Before I talk about that, a little bit about me. Sort of done a whole number of things over the years. Actually started off building Lisp systems back in the late 80s. Eventually ended up programming in Java, wrote the book Pojos in Action, which came out almost a lifetime ago. Started tinkering with this obscure API known as EC2 from an online bookstore back in 2008. That turned into the original Cloud Foundry, which then got acquired by SpringSource and VMware. And for the past 5-6 years, I've really just been doing microservices. That's all I talk about. Well, that and food, actually. Love food, love traveling the world. So I basically do consulting and training around microservices. I have a startup in that area as well. And my book, Microservices Patterns, came out in print back in November. And I think there's the conference discount code where you can get 40% off. I'll show that again at the end. And I also have microservices.io, which I think many of you have probably visited, where there's the pattern language and code and other resources to help you use the microservice architecture effectively, including a recently added assessment tool that lets you evaluate your own microservice architecture. So that's me, microservices, food, yum. So we're going to talk about various different topics, and they all sort of have a sort of kind of visual metaphor, which I managed to just kind of cobble together into a coherent talk. So there's a triangle, there's a cube, there's a hexagon, and then there's an iceberg, but that's a triangle. And then there's cylinders, and then I finish up talking about the testing pyramid. And that's sort of talking about all these different key aspects of the microservice architecture. So I first want to talk about the success triangle, because this, I think, is the motivation for using the microservice architecture. So, a while back, someone coined the phrase, software is eating the world, which in other words, every company needs to become a technology company. And it doesn't matter what you do, whether you're an airline or a mining company, software is becoming increasingly important to the products and services that you deliver. It's all about software. And then you combine that with the fact that the market within which you're operating is basically, in many places, becoming extremely sort of volatile, uncertain. Threats are coming out of nowhere at you, which then leads to the need to actually innovate at a much faster rate, sort of tying into the themes of the keynote. And what that means for us as IT people is, well, we need to deliver software much more rapidly, frequently, and reliably than we have done before. And Adrian talked about this in the keynote, right? Like, it's no longer good enough to have a release like yearly or every 6 months or even monthly. And you can actually quantify rapid, frequent, and reliable delivery with a few key metrics. So there are some velocity metrics like lead time, minimizing the amount of time, minimizing the time from a commit to that code actually being deployed into production. You can measure the deployment frequency. So we obviously want to minimize the lead time and increase the deployment frequency. So we want to go faster. We also want to be much more reliable as well. So we want to minimize the percentage of deployments that cause an outage. And then if there is a problem, we want to be able to detect it, diagnose it, and fix it much more rapidly, which kind of ties into the talk earlier about, say, the use of ML or AI and operations. So there's a need for speed and reliability. And then on top of that, if we are successful with the applications we build, they have a nasty habit of living for a very, very long time. Probably some of the people in the room have been working on Java applications that are basically as old as Java itself, or certainly the early 2000s, right? Or if you're really lucky, you're working on a PL1 application. And I think I read about that language in a history book somewhere, right? I mean, it's old technology, which on the one hand is fantastic. It means that that application was super successful, because there's nothing worse than building an application and going out of business, right? But the problem you have is that technology changes, and you want to be able to modernize your application. You don't want to be stuck using increasingly obsolete technologies. So I sort of view what you need in order to deliver software quickly and sort of for these long-lived applications is requiring a combination of three things, which is what I call the success triangle. You need to have the right process, development process, you need to have the right organizational structure, and you need the right architecture, because it turns out the architecture needs. You have to have the architecture to support the process. You've got to have the architecture to support the organization. That's just basic Conway's law. And what that translates into today is, from a process perspective, your product development methodology is primarily lean, right? Making lots of small bets and trials in the marketplace and rapidly iterating on that. That's sort of the product development methodology. And then in terms of your software delivery methodology, you want to be using DevOps, right? Which is essentially a methodology for delivering software rapidly, frequently, and reliably, a set of practice or principles and practices. And it embraces agile concepts, continuous delivery, continuous deployment, and so on. So that's the process side of things. And then on top of that, you have to have the right organization. And this came up in the keynote as well. You want to structure your organization as small, relatively small, say 6, 8, 10 people, the so-called 2 pizza teams that are cross-functional. So they have all of the capabilities on them to take a concept and turn it into deployed code running in production. And those teams also need to be loosely coupled. So lots of interactions within the teams, but minimal interactions between the teams, because interactions between the teams means scheduling meetings, which means finding a meeting room, which I think, as many of you know, is quite difficult. It's one of the biggest problems in corporate life today. It's universally true around the world. So then it's like, well, what's the architecture? Now, obviously, I'm talking about microservices, so you know the answer to that already. But I'm going to explain why, and I'm going to do that using the scale cube. So we want to do DevOps. You want to have autonomous teams, and you're developing these long-lived applications. Those goals actually place requirements on your architecture. DevOps actually requires an architecture that is highly testable. So has to have well-defined behavior. It needs to be straightforward to test, and the tests need to be to execute quickly. It also needs to be deployable, because you're constantly pushing changes into production, which requires a high level of deployability. Plus, software just generally needs to be maintainable. And then autonomous teams, right, which are loosely coupled, require, according to Conway's law, an architecture that is actually loosely coupled in itself. So you've got a loosely coupled modular architecture, and that will enable your teams to be loosely coupled as well. And then long-lived applications require an architecture that's also modular, because you want to be able to incrementally upgrade parts of them And then combine that, you need an architecture that's evolvable. So you need an architecture with those characteristics. Now, if you go look at a standard application, and most applications I built over the years look like this, right? They had a monolithic architecture. Internally, they were layered and they had modules and so on, but everything got packaged up as a single deployable unit. In the case of Java, that was a WAR file. Before that, it was an EF file, right? And so that's the monolithic architecture, which in itself is not an anti-pattern. It is a perfectly good choice for an application architecture. I actually find that I travel around the world and I actually spend a whole bunch of time going, no, just use a monolith. It's okay, right? Because a monolith can be highly testable, highly deployable, highly maintainable, and so on. It can work just fine. And so you can deliver software rapidly, frequently, and reliably. But the problem that you run into is that applications have a habit of growing. So, we don't stop doing development and do this maintenance thing that they talk of in software engineering textbooks. Development is just ongoing. So the application gets bigger and bigger. Every developer's committing their 20 lines of tested code a day or whatever the metric is. Forget the exact number. But anyway, you have enough people and then give them enough time, and the application's just going to keep growing and growing and growing. And the development team, if you're making money, will get bigger and bigger. So it started off with 6 people sitting in one room, and before you know it, you've got 100, 200 people, so on and so forth. And you try to divide them up into teams, but they're all contributing to this massive code base. So that's a problem. The larger the application, the more difficult it gets to do anything with it. And then on top of that, and sometimes because of that, modularity starts to break down. And so what used to be this sort of pristine, layered, modular architecture just degenerates into a big ball of mud. Haphazardly structured, sprawling, sloppy duct tape. And I don't know, does anyone recognize their application in that description? And then on top of that, the technology choices that you made at the beginning of the project are getting increasingly out of date. And because it's just this massive code base, it becomes prohibitively expensive to rewrite it to adopt a new technology. You might have listened to Adrian and gone, gosh, I want to use Golang because Adrian said it was cool. And Google uses it, which makes it even cooler. But if you've got some ancient code base, you cannot just start using Golang inside your monolithic architecture, nor should you, because it's really just C with garbage collection. Sorry, I just had to get that out. It's just been inside me all morning. I had to get that out there. No, it's good for low-level stuff, but it's not good for enterprise applications as far as I'm concerned. Happily be convinced otherwise. Anyway, back on track. So your technology stack is getting increasingly out of date, and it's difficult to upgrade it, right? And as if you're programming in PL1, you would know this. So you sort of have this picture. Over time, your application is getting bigger and bigger and bigger, and actually much more valuable, which is good. But at the same time, the desirable attributes are getting worse and worse and worse. So development just tends to slow down. And to make matters worse, over time, with the marketplace being more competitive, the desired attribute where you need to be is getting higher and higher and higher. So there is this risk of disruption, right? You can't deliver software quickly enough to compete in the marketplace. Like in Hong Kong, 8 virtual banks were licensed, right? One week, and so suddenly HSBC, the incumbent bank, now has these new competitors. There's an insurance company that's offering hourly commercial insurance for gig economy workers like Uber drivers. Now, how long if you work at an insurance company, how long is it going to take you to adapt your ancient legacy systems to offer hourly insurance? I suspect it would take a while. So you risk being disrupted. So that's the issue you have with the monolith. It's not inevitable, but the probability of ending up in this situation is actually quite high. So that then leads to this, to the microservice architecture. And I first got interested in this like roughly 10 years ago when I read this book, The Art of Scalability. And in the book, they had this three-dimensional model of scaling. So there were three ways of scaling your application. X-axis scaling, which is where you're running multiple instances of your monolith behind a load balancer, everyday kind of scaling, to deal with transaction volumes and availability. Z-axis scaling, where you have a load balancer sitting in front of your monolith, but it's using an attribute of the request to do the routing, or perhaps routing as it's called in some places. So some customers get routed over there, and other customers get routed elsewhere. And that's good for dealing with transaction volumes, data volumes. Your search service, you might, like at the database level, that would be called sharding. But then there's this y-axis scaling, and that is functional decomposition. So instead of what would otherwise be a single application, you apply y-axis scaling and functionally decompose it into a set of smaller applications, which also go by the name of services. And it's a sort of obvious idea, except when I read it, it was like, wow, you can do this? And it's totally resonated because the original Cloud Foundry that I built was this monolith, and we had a whole bunch of development and operational challenges with it. And had we applied y-axis scaling to it, it would have been a lot simpler. So that's why I got super interested in that. And then eventually, this is what got called the microservice architecture. So I like to think of that as an architectural style that structures the application as a set of services. I don't actually like the word microservice because that makes you think of micro, which is small, and these services are not necessarily small. I mean, they should be highly maintainable and testable. They obviously need to be loosely coupled in order to support the loosely coupled teams. They should be independently deployable. They typically implement business functions or capabilities, and they're owned by a small team. So your small autonomous team will typically own, ideally, just one service. I think that's an excellent starting point. So rather than sort of going down the path of having these super fine-grained architectures where you have like one service per developer, because you heard about that in like a Uber presentation or something, you should really start off with a fairly coarse-grained architecture. And quite often, just having one service per team is sufficient to meet those architectural requirements that I mentioned earlier. And you should only introduce more services if it solves a problem. Like maybe this service has got too big and testing takes too long, so that might be a reason to split. Or there's some other non-functional requirements that you need to satisfy. So, but I do like the idea of one service per team. So the food-to-go application, sort of rethought of as a monolithic application, or as a microservice application, would look like this, where you've got a bunch of services, each one of which implements a business function. Each service has its own database. That's important for loose coupling, which I think I will talk about later. The services might communicate using synchronous protocols like REST or gRPC, but they, for reasons I'll get into later, will often communicate using an asynchronous messaging protocol and using a message broker. You could functionally decompose the UI, having different web apps focused on different parts of the UI. You might have an API gateway sitting in front of your services, which exposes the public API, which in this example is consumed by JavaScript running in the browser and a mobile client. So interestingly, lots of moving parts, which is one of the drawbacks of this architecture. So that's the microservice architecture. And you want to do it because it improves testability, right? The fact that these services are relatively small makes them easier to test. They're independently deployable by definition. Because they're small, they're easier to maintain. The code should fit in a developer's head, right? Shouldn't be cognitively overwhelming, which is the problem with a monolith. It's an inherently modular architecture. You can't bypass a remote API and access the internals, so it does a much better job of enforcing modularity. Unlike, say, in Java, where basically every public class on the class path can be accessed regardless of any notions of module that you might have put in place. And it is highly evolvable as well. You can upgrade the technology stack one service at a time. You can run an experiment. You can try using XYZ language. And if you like it, that's great. And if you don't, it's not a disaster. You can swap it out at some later point. So, a lot of benefits. And I like to kind of relate that back to the success triangle, right? The microservice architecture gives you the testability and deployability that you need for doing DevOps. It gives you the modularity and the loose coupling that you need to support the autonomous teams. So it supports Conway's law there. And then it also gives you the modularity, the evolvability, and the maintainability that you need for these long-lived applications, because you can upgrade it piecemeal. Obviously, there's downsides to this, and for the sake of full disclosure, I'll mention them briefly. Right? By far, it's a much more complex architecture. You're building a distributed system, so you've got to deal with inter-process communication, distributed data, partial failure, and all the other complexities of distributed systems. There's some interesting challenges around testing, and trying to avoid doing end-to-end integration tests. And it turns out that consumer-driven contract testing that was covered earlier is one of the key things there. Deployment is much more complicated because instead of a single application, you've now got potentially tens or hundreds or thousands of applications, many instances of each one, so there's many more moving parts in production that need to be monitored and managed and so on. So there's a bunch of complexity there. And then there's challenges around correctly drawing the service boundaries. And it's really bad because if you get it wrong, you end up with a distributed monolith, which is like the worst of both worlds. And then it's actually challenging to adopt this architecture. Taking your legacy system and breaking it apart into a set of services is just this hideous, painful process that can take many years. But many companies have gone down this route and have experienced microservice nirvana when they've got to the end of it. But it is a painful thing. Okay, so that's the microservice architecture defined. I now want to sort of dig a level deeper into that and look at the structure of an individual service. And for that, I'm going to introduce the notion of a hexagonal architecture, which not a new idea. It's been around for a while. We love our three-layered architecture, right? Where we love to draw pictures like this to explain the structure of our application or service. So we've got presentation layer, business logic, persistence layer. But this architecture doesn't exactly capture what's going on. Like, it actually says that the business logic layer somehow depends on the persistence layer, which often is not the case. It's often the other way around because the business logic exposes an API that the persistence layer implements. And then it doesn't properly support the notion that you could have multiple presentation layers, multiple ways of handling inbound requests or having multiple persistence layers. So it's all a bit, even though it's super popular, it's all a bit funky in terms of how it works. So for that reason, I actually like the hexagonal architecture. And it's an idea that's been around for a long, long time. Basically, it looks pretty as well, which is really important. Though it doesn't fit on slides that well if you've got lots of them. But anyway, so it puts the business logic at the center of the application or the center of the service. The business logic is actually exposes a number of ports, which you can just think of in Java as just being interfaces. So some ports are inbound ports that let the outside invoke the business logic. Other ones are actually outbound ports that are interfaces that enable the business logic to invoke other things, like access the database. The other part of this is there are adapters. And this is also known as the ports and adapters architecture. So the adapters are classes or clusters of classes that either handle inbound requests. So these could be in like the Spring Framework controller classes, which handle HTTP requests, or they can be like database access objects that enable the business logic to access the database. The order controller invokes the port, and actually the database access object would be a class that implements the outbound port interface. And you can have other adapters for like interacting with message brokers and making HTTP requests, like proxy classes and so on. So I like to think of that as being not only, that could be the structure of your monolithic application, but it could also be the structure of your service as well. So in the context of a service, it looks like this. So the whole point of a service is really to expose an API to the outside, to its clients. That's its whole reason for existing. So the API consists of two parts. It has operations, which can be invoked by the clients. There's two types of operations. There are commands that change data, like create order, revise order, cancel order. There are also queries that retrieve data, find order history, and so on. So that's the operational part of the operations of the API. And they can be invoked either synchronously, using REST, gRPC, or they can be invoked asynchronously as well. The service can also publish events. That's the other key part of the API. So those would be DDD, domain-driven design, domain events. So when data changes, order created, order revised, order canceled, the service could emit an event. And then the service could also invoke other APIs, or APIs of other services as well. That's quite normal in some senses. And it can also consume the events that are emitted by other services. Here's an example of that. So, here's the order service. It implements the create order operation as a REST endpoint, post/orders. It actually emits order events like order created. And then it interacts with other services, actually asynchronously, for reasons I'll get into. Synchronous communication is best avoided. So it interacts with the consumer service and so on. And then it also consumes events that are emitted by the restaurant service. And I'm going to talk about some of these details in a little while. But that's sort of an example of a typical service. And I talk about this in more detail in my book, shameless plug. There's also an operational aspect to a service. In order for it to be production ready, it has to implement other sort of capabilities, which you can think of as adapters as well. So number one, it needs to support externalized configuration. Configuration values, such as which database to connect to and what credentials to use, need to be passed into the service at runtime. So there needs to be an interface, so to speak, for doing that. It might be as simple as merely reading environment variables, or it might be a bit more complex as, say, reaching out to a config store and retrieving its values, this sort of push and pull models. But that's one key capability that a service needs to implement. It also needs to implement logging, which is basically logging to standard out in some standard format so that the runtime infrastructure can then aggregate the logs. So that's not too complicated, but you just have to log. Pick one of the numerous Java logging frameworks for that. It should also implement a health check endpoint that enables the runtime to verify that a service instance is actually ready to handle requests and also and continues to remain healthy. So that could be like /health/HC or /actuator/health. So if you're running on top of Kubernetes, that would be the liveness or the readiness probe and the liveness probe. And if your service became unhealthy, that would start returning something other than 200. Kubernetes would eventually kill it off and restart it. So you've kind of got this self-healing system. The service also needs to expose telemetry as well, gather metrics and report those to some metrics collection system in some form or fashion, whether that's AWS CloudWatch or Prometheus, some data gathering system where those metrics can be stored, aggregated, visualized, and you can set up alerts on that. And then the last part, it needs to support distributed tracing. So in every inbound request to the system gets assigned a request ID or trace ID that then services that get invoked would then propagate that from any inbound request to any outbound requests and actually report back to a distributed tracing server. That lets you visualize the flow of requests through the system and do troubleshooting. Plus the tracing ID will actually end up, the trace ID will actually end up in log messages as well. And then if you're using log aggregation, you can search for a given trace ID and see all of the log entries that were generated while handling that request. Really simple, but a good debugging tool. Okay, so that's the structure of the service. And I kind of want to move on and talk about another shape, which it's a triangle, but the metaphor here is iceberg, which I assume are triangular in shape. So remember, the services need to be loosely coupled. Though interesting, there's a couple of different meanings of the term loosely coupled, but among other things, right? The teams need to be loosely coupled, which then, according to Conway's law, requires the services to be loosely coupled as well. So there will be some coupling because there's collaboration, but it needs to be kind of minimized. There's two different types of coupling. There's runtime coupling, which is where one service synchronously invokes another one. And that actually impacts availability. And I'm going to talk about that later. In this section, I want to talk about design time coupling, which is where if a change gets made to one service, like the customer service, you don't want that regularly impacting its clients, the services that depend upon it, because that requires a lot more coordination and communication between the teams, which sort of destroys the autonomy of those teams. So you want to make sure that you have well-designed, stable APIs that encapsulate the implementation of the service. And I like to use the example, like, say, from Stripe payment system, right? Where there's sort of, I know it's more complicated than this, but fundamentally there's an API, or endpoint, which is like, charge this credit card. Really simple API, but behind that is a massive amount of complexity. Or with Twilio, like, send this SMS. Simple API, but presumably there's a lot of complexity involved. Those APIs are great abstractions that hide quite complex implementation. So you want to make sure that you want to design APIs similar to that. And you also want to avoid shared libraries as well. If you implement business logic in a shared library that's used by multiple services, if the corresponding business rules ever change, then all of those services have to be updated in lockstep, which destroys the autonomy between the teams. So that's not good. So I like to think of you designing services that look like this, and I call them icebergs because presumably what's visible above the water is quite small relative to what's below. So you want to have these small, stable APIs that encapsulate a complex implementation because that enables the teams to change the implementation without regularly having to change the API, especially in ways that are incompatible, which then requires the consumers to be changed. And you want to avoid services that look like this, where they're sort of all API and no implementation. And a good example of that are these services that just wrap a database schema. And the API basically mirrors that database schema. And there are tools that are really good for generating this automatically. So you can auto-generate a badly designed service architecture just like that. Don't use them. Services should actually contain data and business logic, and should ideally have a lot of complexity that's encapsulated by a simple, stable interface. You want to avoid database tables or sharing of database tables because that is basically tight design time coupling. You know, if the order service was accessing the customer service, whenever the customer service team changed that schema, the order service would have to be updated. And it would just be bad for everyone. And it also introduces runtime coupling. So don't share database tables. Just encapsulate the data, access it through APIs. How am I doing for time? Gosh, behind schedule. All right. So the next thing I want to talk about is another kind of coupling known as runtime coupling, which is where services communicate synchronously. And so there the shape is a cylinder, which is the sort of visual representation of a message channel. So the solution is asynchronous messaging. But let's kind of have a quick look at the problem. So imagine you wrote something like this, where you have an order service, a post request comes in to create an order. The order service then makes another post or put request to the customer service, sits there waiting for a response to come back. And then when it does, it finishes up and returns a response. Super simple. But the problem you have is that you cannot create an order unless both these services are available. So the availability of this API is the product of the availability of the two services. And if there were more services involved, it would be service availability to the power n, which rapidly becomes not that highly available. And this is sort of an example of this anti-pattern where you go, well, we've got a bunch of modules in my monolith, and we're now going to just turn them into services, and they're going to communicate in the same way with a lot of synchronous inter-process communication. That's generally a bad idea. You now have multiple points of failure in your system. It will become very brittle. So you want to use asynchronous messaging. And there's an excellent book, Enterprise Integration Patterns, classic book. And I guess Gregor's speaking later today, right? So yeah, go buy his book, because it's awesome. But that's the abstraction of messaging systems. Services communicate by sending messages via a messaging channel to some other service. And these channels are basically sort of abstractions over what the message broker provides. So they could be Kafka topics, JMS queues, JMS topics, and so on. And there's different types of channels, like point-to-point or pub-sub. So then, okay, so we're going to use messaging. Well, what does the order service look like? So one strategy, one design approach is to use sagas, which is like this whole other talk, or multiple talks, but it relies on asynchronous communication. So the way an order would get created is as follows. Post request comes in. The order service actually returns immediately. So it's telling the client, hey, I've accepted your request to create an order. The order ID is this. Check back later to see whether the order has been approved or rejected. And then the services exchange messages. In this example, it's events, which is a choreography-based saga. There's also orchestration-based sagas. And then the messages go back and forth, and the order gets approved or rejected. And this is nice in the sense that availability is much better. The order service can actually accept the request to create an order without actually being dependent upon any other service. But you've got the complexity of sagas. Chapter 4 of my book, by the way, very detailed explanation. And then the other problem you have is that the response doesn't say whether the order has been approved or rejected, which makes the client more complicated. The other option is to use replication, which goes by the name of CQRS. So here, the credit limit is actually replicated to the order service, and the order service is responsible for keeping track of the available credit. Even though that's part of the customer, the responsibility for it has been moved to the order service. So that means the order service can actually validate orders without having to interact directly with the customer service. Instead, there's replication through events. So availability is improved, which is good. The response actually contains the outcome of validating the order because it can check available credit there and then. But now you've got the cost and complexity of replication, which I like to think there's only 20 million people or 25 million people in Australia, so that does put an upper bound on the number of rows in a table. So, yeah, country-specific cost of replication there. Okay. You know, whereas if you're Facebook scale, replicating with billions and billions of users, replication would be way more expensive, obviously. Anyway, just a thought. So a couple of different approaches, both leveraging asynchronous messaging, which with some downsides, but gives you a system that's much more available. And there are some people who are adamant that you must not use synchronous communication between your services. And I would certainly agree for updates, you should really, really avoid it. Queries, you can make it work. So the last thing I want to talk about really, really quickly is another triangle, also known as the testing pyramid, which Beth talked about earlier in her talk. And I have one that looks slightly different, I think. But one thing I want to point out is, microservices are there to enable DevOps. DevOps requires automated testing. Not only that, microservices are complicated and need automated testing. So if you attempt to do microservices without automated testing, it is self-defeating and it is risky. And sadly, I've encountered quite a few companies that have gone down that path. And there's an anti-pattern I wrote about, which is the flying before walking pattern, where they haven't mastered the basics, like automated testing. And interestingly, there's some surveys that bear this out. It's like 72% of companies do not extensively do automated testing. And ironically, it's like 90% of companies want to do DevOps and Agile, which require testing. So there's this total disconnect between the two. And I said this to Kent Beck when I met him like last December. It's like JUnit is 20 years old, and it's sort of like, hey, Kent, when do you think this automated testing thing's going to catch on? Right? So we need to do better in that regard. And this whole concept of a testing pyramid is super important, right? So it's showing the relative proportions of the types of tests that you need to implement. And you want to push the testing down to the bottom of the pyramid as much as possible, because those tests, like unit tests, which are in memory, are incredibly reliable. They don't fail randomly. They execute really, really quickly, and they're simpler to write. Whereas at the top, it's much more complicated to write the test. They're really slow, and they fail just randomly, just because. So that's one key concept. And obviously, the path from developer machine to production is a deployment pipeline. And you really want to, you will have one deployment pipeline per service. That's kind of a key thing. So every team is working independently, developing, testing, and deploying their services independently. I was going to talk about consumer-driven contract testing, but Beth covered that really, really well. So I will not, in the interest of time, repeat that, except that I like to use the Spring Cloud contract testing framework.
What chapter is that?
Oh, actually, I was so excited about testing when I wrote my book that there were actually 2 chapters on testing. I can't remember their names, but anyway. But one thing I want to talk about, which kind of builds on what Beth talked about, is just this whole, we want to have end-to-end testing, because, yeah, that's how we actually verify that our system works properly, right? You can do it, but I think it's, as they founded REA, I would strive to eliminate that and just rely on per-service testing. And not have this sort of roadblock in the way, because you think about it, right? You want to fix a bug in production, it has to go through your deployment pipeline and run through end-to-end testing, and that's just going to slow you down, especially if there's random failures and requiring restarts of builds. So I want to finish with this thought, right? Which is, this whole concept of testing in production, or a better way, which is maybe more acceptable, validation in production, right? So the idea is, there's a bunch of separate ideas, but one of the ideas is that you separate out deployment, which is the act of getting the code running in production, from release, which is making it available to end users. So you can have code running, but it's not actually released. Plus comprehensive monitoring of your services along with a high level of automation so that you can quickly deploy or roll back or roll forward your changes. So one strategy is to use a canary deployment where you deploy version 2 side by side with version 1 behind an intelligent traffic router, which could be a service mesh like Istio. It's great that there's open source projects for this. And initially, it's not getting any traffic. You could test it. Then you could route some traffic from test users, maybe internal users, to it. And then you can route a small percentage of production traffic to it. And then you gradually turn the dial, routing more and more traffic to it until eventually it's got 100% of the traffic. But you're actually kind of connected in with the monitoring system. So if you see excessively high latency or 500s or anything like that, you can flip the switch and actually automatically roll back to just version 1. So that's kind of the modern way of doing deployments, where you're testing in production. And there's sort of a whole bunch of writings about that. Cindy Sridharhan at CopyConstruct has written some interesting posts about that. Anyway, that's pretty much all I have to say, which is good because I'm out of time. But one last thought. In summary, right, the goal is rapid, reliable delivery of software, frequent delivery of software for these long-lived applications, which has architectural requirements which are often just met by the microservice architecture. Hexagonal architecture is the structure of your services. You want to design services that look like icebergs, so you have loose design time coupling. You want to use asynchronous messaging so that they are loosely coupled from a runtime perspective. And you want to make use of the test pyramid and push as much of the testing down the pyramid as possible. and try and avoid end-to-end testing as much as possible. So thank you for listening. Hope that you found it useful. And please take a look at my book. Thanks.